resistance can then be input at 15 extra resistance in the section in which it occurs. The impact of this can then be studied in the produced output data as to any favorable or unfavorable result. Alternatively, the skirt board length itself can be corrected at 17 skirt board length, also in sections input data. Sections is a drop down from right edit at the menu bar. Title 14 identifies idler space limitations under running conditions. Working this information in conjunction with Title 19 obtains a dollar value to extending idler space. The user is again cautioned that these are running condition recommendations and that warnings for any stopped acceleration or deceleration condition should be taken seriously. This is first indicated at the optimization action plan. Title 15 reconfirms shaft factors entered. These are based on steel grade used. Users should be certain that the steel grade entered is actually in use. Title 16.1 displays shaft diameters required, both at the bearing and at the pulley hub bushings. This information, the percent of belt strength rating actually used or utilized at each pulley is displayed in the right-hand column. This percent, worked in conjunction with belt manufacturer's information, provides a minimum pulley diameter recommendation. A SEMA-based recommendation is also available at Title 16.3. Title 16.2 provides results helpful to selection of gear reducers and bearings. RPM and torque are based on diameters taken to the center of the belt tension cords. At dual drives, a slight difference may exist in RPM for pulleys of the same diameter resulting from belt stretch. Normal motor slip is usually forgiving of this. In some older dual drives connected by fixed gearing, equal diameters create a problem evidenced by the belt bunching up. Title 16.25 provides dynamic bearing loads to assist bearing selection. Title 16.3. The program scans essential data, and if published requirements are not met, Title 16.3 provides warnings that should help avoid what are usually the largest repair and business interruption costs of belt conveyors, namely failures related to belt splice and pulley strength. Pulleys serve to support, change direction, transmit motion and force to the belt. Pulleys and belt must work hand in glove. The pulleys must not be too small in diameter as to cause undue bending stress in the belt, and the pulleys must be of sufficient strength to resist belt tension. SEMA, pulley, and belt manufacturers have established standards. Working these standards within the output data of the particular belt conveyor is the purpose of Title 16.3 and Title 16.1. In Title 16.3, input pulley diameters are listed in column entitled Actual Pulley Diameters. These were put into the input file. The input pulley diameter is sufficient if it exceeds the diameter under minimum diameter required to limit belt bending. In this case, it does not. 24 is less than 31. So we have a diameter problem. And therefore we have the yellow signal. If the input pulley diameter is less than that required to avoid using a heavy-duty pulley, then a heavy-duty pulley is required. Let me review that. We have input a 24-inch diameter pulley, but the belt requires a 31.2-inch diameter to avoid belt bending. So we require a larger pulley. We don't meet that requirement. The minimum diameter required of a standard pulley is 32, but our pulley diameter is 24. 24 is less than 32, therefore a heavy-duty pulley is required. The consideration here is that to avoid a heavy-duty pulley by going to a larger pulley, and since this is a drive shaft, this will also create more torque and therefore a more expensive drive. There are a number of considerations here. The belt bending requirement must be met, and in this case a pulley larger than 24, probably 32. That may avoid the need for an engineered class pulley, but at the same time the torque at the reducer goes up. This intends